Okay, well, thank you very much, Robert, for this very, very nice introduction. It's been my pleasure to visit and see some really hugely impressive setups and have good discussions here, especially the things that are kind of underway that are being constructed at the moment are really, really cool. And I hope you'll agree are very complementary to some of the things that I'm going to talk about. So what I'm going to talk to you about is this new technique of terahertz scanning tunneling microscopy. I'm not going to dive right into it. I'm going to have some background to try to make sure everybody kind of understands how it works. If you are already an ultra fast researcher, it might be some stuff you already know, but I hope sometimes I like hearing things I know. Okay, so to start with, I'm hoping this clicks. No. Let's see if I click a button, then it'll work. Okay, first problem solving. Sorry, just a moment. Okay, so first of all, one of the first things I did when I got my position at MSU is I went and I stood outside the football stadium and I took a picture of myself, or had my wife take a picture in this case. I think I probably should update this on the other side of the fence at some point. You can see I just kind of blocked out. But this was just to give people an idea of where Michigan State University is. You can see right here in East Lansing in Michigan. If you ask someone from Michigan where they live, they'll hold up their right hand and they'll point, right? You can kind of see why, because it looks like a little mitten. If you want to go on vacation, you can hold up your left hand, and you can go to the Upper Peninsula, right? Or if you want to look for yourself, then you can look at the back of your left hand. Okay, so first thing I want to do is highlight the folks in my group who I work with. I'll show them again at the end, but just so you get a sense of what our group is. You can see me there, Stephanie, who's a PhD student who's done a lot of good work that's coming in towards the end. Sheng and Mo are the senior grad students now. Vidrin, he's been a postdoc with me, and he'll actually is a character that will come up in this story a couple times. Larry was a sabbatical visitor from Taiwan that we're continuing some collaborations with. And I have a new grad student, Kaden, and an undergrad student, Austin. And then, of course, this is sort of the second generation, I guess, of the people in my lab. Eve Ammerman especially did a lot of the good work in building up originally. Okay, so this is my outline. First, we're going to learn about ultra-fast science, or we're going to be refreshing ultra-fast science. And then I'm going to explain to you how this technique that I want to talk about works, okay? I'll lead from that into one of the first things you can do, which is look at single molecules, and then tell you some of the more interesting recent things I've done at MSU with new platforms that might be interesting for future technology. Okay, so first of all, let's just give sort of an example of why we might be interested in doing ultra-fast science. So these are kind of bird's eye view things, not necessarily things that I'm working on. But for example, I teach a class at MSU, which is Introductory Physics for Life Sciences majors. And we've kind of adapted our colloquium or our curriculum a little bit to try to be talking about things that are relevant for them. So one thing that we cover is actually photosynthesis. And in that part of the class, we learn about how light is absorbed in these different light harvesting areas, and the excitation actually migrates to a reaction center. So if you think about the time scale of this can actually be on the time scale of picoseconds. If we instead think about something like technology, one of the most obvious things when we're talking about light matter interactions and fast timescales is what happens after light is absorbed in a solar cell, for example. So light comes down, you have, let's say, electron hole pairs created in a semiconductor. They might create an exciton, right? A bound electron hole pair, that's like a little hydrogen atom. That can be dissociated. Those can break apart. And the way you get your photovoltage is you harvest one, from your donor to your acceptor. You break them apart, and then you can actually get some photovoltage. Okay, so again, these are something that happens on what we would call ultra-fast timescales. So there's a number of motivations for why we want time resolution. But what do I mean by ultra-fast? So here's my little intro to timescales, let's say. So I've got here 1 nanosecond, 1 picosecond, 1 femtosecond. So this would be kind of like the clock rate of your computer. And this might be the time scale of some photoexcited nanosystem or semiconductor system. So this is what I'm talking about, picoseconds to tens of picoseconds, 100 picoseconds. If I had an ultra-fast laser pulse get excited by gallium arsenide, this is kind of how long that excitation lasts. If I go faster, then I start thinking about internal vibrations, maybe the motion of atoms inside a crystal, like phonons. And if I go even faster, I could think of the oscillation period of visible light. So if I had an 800 nanometer laser, for example, that would be about a 2 femtosecond oscillation period. So this is pretty fast, and this is ultra fast, okay? Now, sometimes these ultra fast techniques, we're studying things kind of in this range, and what we're referring to is often the time resolution, right? Of course, there are also people here doing attosecond science, which is down here. I won't cover it in the talk, but of course, that is even faster, right? Okay, now just to kind of set the stage, one of the most common things we do in ultra-fast science is what we call stroboscopic pump probe measurements. And the trick is that these light pulses are really kind of the fastest things around, so you need to use them to measure each other. So it's not like you can just photoexcite something and then just read out electronically what happens. Instead, you photoexcite something and then you use another pulse to measure what happens. So here's an example. So here's my pulse, and it's going to go through this box, right? Now here comes a different pulse. This pulse is red, and it makes this red. So imagine that red pulse excited the sample. Then the black pulse is going to probe what happened to the sample. But we need to do this basically over and over again. So what we do is we say, how much of the black pulse transmitted relative to when it arrived compared to the red pulse? So we repeat the experiment over and over, measuring the function of where that pulse is. So each of these might be thought of as a different time delay, where here the black pulse arrived first, then the red pulse arrived first, the sample was excited, and then as we take these measurements at different set time delays, we see the recovery of the system. So in this way, we build up sort of an average response of that photoexcited system. You could imagine like someone is going to throw a baseball and they're so good at throwing it. They throw it so fast that you can't get a camera or can't get a video camera that can capture it. So instead, what you do is you have a strobe light and you have some set time delay, and some time after they throw it, you do a strobe light flash in a picture. You just make them throw it a million times. And then you build up that picture over time. That's how you do this, except it's very, very fast, right? Okay. Now, I am specifically going to talk about terahertz, right? You heard this term already, terahertz. So we need to make sure that we kind of orient ourselves on the electromagnetic spectrum and think about what do I mean by terahertz. So we've got the visible, where I've kind of the wavelength here and the frequency. If we go beyond what we can see in visible, we go into the near infrared and then the mid infrared. Historically, we used to call this the far infrared. Terahertz and far infrared are basically the same thing. And we go past this, we can get into the microwave range. So if you're more used to thinking about an energy, you can think here, we're kind of the electron volts range for visible light. 1 terahertz is 4.2 millielectron volts. So kind of orient yourself on this scale. Now, historically, terahertz was sort of an underexplored region compared to the things on either side. So at lower frequency, in the microwave, you can make strong coherent sources of light using electronics, right? You have a microwave, you can put a hot dog in it, etc. At higher frequency, you could use photonics, i.e. you could make a laser, right? This region, it was hard to make strong coherent sources of light. So this, for a while, was called the terahertz gap. And so although there were many interesting material excitations in this frequency range, it was less explored, right? Because it was hard to make some strong coherent source. Now, we can kind of easily get into this range. And what we do is we use a trick. We start with a ultra-fast near-infrared laser, which we can purchase. And then we use nonlinear optics to frequency down convert it, generate these terahertz pulses. Although that's kind of taken a while to develop, we get some benefits out of it, such as we can make a pulse of light that's 1 oscillation cycle long and always looks the same. Now that we have these terahertz pulses, and we can use them to explore samples, there's a number of things inside condensed matter that we're particularly interested in. And this is maybe one of the reasons also why it was hard to get into the terahertz range, is because there's so many things going on. So here's a plasmon excitation. This is like I photoexcite a sample. I have 3 electron hole pairs, and I have a collective motion of those charges. The plasmonic resonance can often be in terahertz range for photoexcited semiconductors. Magnons, so collective spin waves. Phonons, collective lattice vibrations. Then there's some more complicated things. I'll highlight this one maybe. So excitons, you can have these little quasi-hydrogen atoms that are made up of a hole and electron that are bound together, and you can have internal transitions of those, just like you would have transitions in a hydrogen atom. Those transitions of an exciton material, their transitions are in the terahertz range. And the reason is their binding energy is scaled down compared to what you would think of for a hydrogen atom. Now, in terms of making these terahertz pulses, I alluded to this already. We can start with a near-infrared pulse, and there's a couple kind of easy ways that we generate this. One is we use a crystal that is not centrosymmetric. It has some polarization response that responds as the square of the electric field. And then the second derivative of this polarization response is emitted light, just from our electromagnetism class. And so we get terahertz pulse out. Similarly, we could have a photo switch. We could put a voltage across it, and then if we short circuit that photo switch, you get a very fast current that emerges, and the derivative of that is the emitted terahertz. So these are a couple of ways we can make these terahertz pulses, and we can detect them in very similar ways. We can either use a nonlinear crystal again, and use a near-infrared pulse to read out how the terahertz field affects the crystal, basically puts a polarization rotation on the near-infrared pulse, or we can read out some current. So those are kind of our conventional ways to generate and measure terahertz pulses. Now, there's a challenge. So I started my PhD doing terahertz spectroscopy. That is, I have a sample, I would pump it, I would pass terahertz through, and I would see how that terahertz was affected by those material excitations. Now, I was interested in nanoparticles. The trouble is, if I take terahertz light and I try to focus it down, the smallest focal spot that I can get to is restricted by the diffraction limit. This is if we think of our Gaussian optics, right? What's the tightest I can focus something? This is roughly half the wavelength. So for visible light, that might be something like 200 nanometers. You can make a really nice microscope and get reasonably good resolution. That's, let's say, with blue light. For terahertz, the wavelength of 1 terahertz is 300 microns. So we're talking about, at best, 100 microns, practically more like a millimeter. So that says we're doing pump probe experiments. We might be sensitive to very important material excitations inside nanoparticles and things like that, but we're looking at something on a macroscopic length scale, and we might want to look much closer, especially if we're interested in nanostructures. Okay, so how do we get around this? So this is kind of a little zoom in on achievable spatial resolution that you can get by adapting how you measure things with terahertz light. So to start with, this is my focus, right? I focus the terahertz down and I get to the kind of 100 micron scale. What you can then do is integrate what's called scanning probes. So the first thing you might think of is a little pinhole in a metal screen, right? And you could move that pinhole around. Not too much terahertz is going to go through that sub-wavelength hole, but if you get really close, then you can kind of get a better resolution than you would have otherwise. So this gets you down to the micron scale, but it doesn't quite get you where you want to go. The next step with this is a tip. So it's a sharp needle. It's basically an atomic force microscope tip. And you can imagine this tip is something you're going to move back and forth over the surface. So what happens is the terahertz is focused on this tip. It's like a wire that tapers at the end. And the tip acts like a lightning bolt or like a fork in a microwave. So the terahertz field gets strongly enhanced at the apex. The photons get kind of collected down. They're in this volume that's smaller than the free space wavelength, right? So the way that you can do this is you have evanescent fields that are non-propagating. You can find the light down in the apex. So you could think if you're in your electromagnetism class and you're drawing field lines away from the tip, you draw lots of little charges at that curvature and you get lots of field lines bunched together. So the way this works is you bring that tip close to a sample surface. It acts like a dipole. You have an image dipole on the surface, and the coupled dipole system radiates in the far field. So it's almost like you a little focus the end of the tip, and if you move back and forth over the surface, you can then identify what is happening in terahertz range underneath that tip. So we call this the dielectric function. That's what we're trying to read out, is the terahertz dielectric function. So we can improve our spatial resolution. We can get down to the scale of the radius of curvature of the tip apex. But maybe we want to do even better. So this is where we are at the end there. And this is what I'm going to tell you about today. So this is now, you start basically with this geometry, but you make your tip so sharp that it's atomically sharp. And then what you do is you don't just measure the light that comes out. You turn that terahertz field up so it's very strong. And what it's going to do is it's going to control electron tunneling between the tip and the sample, and we'll measure the current. And so by doing this trick, we can confine what we measure to an atomic tunnel junction and therefore get the benefits of terahertz science, including ultrafast time resolution and sensitivity to terahertz excitations, and we can confine them to an atomically sharp tunnel junction. And by doing this, we can see single atoms. Okay, so this one is called scattering type scanning near field optical microscopy. SNOM would be the abbreviation, so there's quite some people doing this. And this is this one, terahertz scanning tunnel microscopy. Sometimes we throw in this light wave driven thing. It's basically just a decoration. Okay, so terahertz STM is what I'm going to talk about today. So here we have a terahertz scanning tunnel microscopy. So let's learn how this works. So first we know from our quantum mechanics class, we have here some region where we've got a propagating wave that is our electron, and then we've got a potential barrier, an exponential decay of our wave function into that potential barrier. Right? Okay, good. So here we go. This depends on some kappa. This is depending on the height of the barrier. Now, if we go to the next day of our quantum mechanics class, now we have a situation where we have our propagating wave of our electron. Then we have a barrier. This time we make it shorter. It's not infinitely long. We cut it off, and let's say this distance d, and then we get a little bit of quantum tunneling of electron through the barrier. Okay, great. So now we turn this sideways. We've got this atomically sharp tip. We've got a metal that could have an electron inside it. In between here, we have nothing. And that nothing corresponds to a potential barrier. It's just vacuum, but the energy would be lower here or here. So what we do is we look at quantum tunneling of electrons between the tip and the sample. So you can imagine if I made this barrier thicker, that I would have the electron tunneling rate go down quite substantially. The trick to this technique is that it doesn't just go down a lot, it goes down crazy a lot. If you move the tip back by 1 angstrom, so 10 to the power minus 10 meters, it goes down by 1 order of magnitude. So that's how sensitive you are to this tunnel current you're going to measure. So as long as you can prepare a tip that's sharp, that sensitivity to height allows you to trace out a surface with very, very good resolution. So here's basically how it works. You have a tip here, no terahertz pulse scan, and that tip is part of a circuit. So your sample is conducting, and these are atoms on the surface. We apply a voltage to the surface, and we're going to measure the current. So imagine that's just a resistor in our circuit. Then what we do is we're going to move this tip back and forth over the surface, and we're going to see some current. And so we can do it a couple ways. Either we can just look at what is the current as a function of the position, as we kind of snake back and forth over the surface, or we can use a feedback loop where we keep the current constant. And if we do that, then the tip moves up and down, and we call this a topography. Technically, it's not purely a topography. We're mapping out the electron density, the density of states of electrons on that surface. And so by doing this, we can trace out really atoms. Now, if we take a little more kind of like energy side view of these things, what is happening is, here's our tip above our sample surface. And this is a drawing of 3 different configurations, what happens in this case. So here we have the tunnel barrier. Here we have a sample. What I've drawn here are the density of states. So where the electrons can be of the sample and the tip. So here's a tip, and I've got blue. These are electrons filled up to what we call the Fermi level. Then I have the sample, and I've drawn a different sort of density of states, like it's a semiconductor. If I apply a voltage to my circuit, what I do is I unbalance the Fermi levels of the tip and the sample. So in this case, I move the sample states above the tip, and I can have electrons tunnel out of this. This would be the valence band into the sample, or into the tip, excuse me, or vice versa. If I apply a voltage the other direction, I can tunnel out of the tip into the sample. So what I'm doing, I'm applying a voltage, I'm tunneling one direction or the other direction based on where the empty and filled states are. But the cool thing is, I'm also very sensitive to the density of states of the sample. So there's really some physics in there we'll talk about in a second. Terahertz scanning tunnel microscopy, the terahertz pulse acts like a voltage. So this is a weird thing, a little bit, that we'll think about for a second. I have an ultra-fast pulse. I generate it from a laser. Usually when we're generating optical or near-infrared pulses and we focus them on something, we think about photons, right? I absorb something and I have a transition from here to here. The terahertz is very low energy and its oscillation frequency is relatively slow. It's going to act like a voltage. So if it acts like a voltage, what's going to happen is I'm going to oscillate through these configurations as a function of time. Okay. let's go to this picture again for a second. Think about our frequencies. Why can I call the terahertz pulse a voltage? So we need to think about what happens when we have large fields, large number of photons. Okay, if we have small numbers of photons, we think about linear optics. That's kind of our simple. The field doesn't matter when you interact with matter. So now let's think what happens if we have optical light. Let's say we have an electron here down at a potential level, and we send in some light and we want to excite it out of that potential level. But the photon energy is not high enough. But 2 of the photons will be enough. So let's say we send in a high enough intensity that we have a high probability of absorbing 2 photons at once, and the thing will jump out, right? Sounds good. That's what I would call a multi-photon process. But there's another regime that we can think of, which is separated from this multi-photon process by what we call the Keldysh parameter. So this Keldysh parameter is the ratio of the ionization potential of this well to what we call the Ponder motive potential. So if I have an electron in free space, how much kinetic energy does it gain if it's just oscillated by in free space by the oscillating field of the light pulse? Okay, so that ratio defines whether I'm going to be in this multi-photon regime or the strong field regime. So I can put into this equation what goes into that Ponder motive energy. So I have the frequency, angular frequency in this case, the mass of the electron, still that ionization potential, electric field, and the charge. So now imagine that this is Keldysh parameter greater than 1. That Ponder motive energy is relatively low, maybe because the oscillation cycle is switching back and forth pretty quickly. But I can have another regime. And that regime is when this oscillation cycle, you might think of as being a bit slower. When that's the case, instead of thinking of this potential well as absorbing 2 photons and getting ionized that way, I instead can think of my oscillating electric field of a light pulse as being a quasi-static potential that basically bends the landscape back and forth like this. So in this case, what I've drawn there, I've drawn it coming back because that's something you might have seen in the news. So that's how attosecond science works, right? And high harmonic generation, which is the Nobel Prize this year. So basically that's in the strong field regime. Think of this light field that's quasi-statically modifying the energy landscape, leading to, in this case, field emission or ionization, right? Now, the cool thing here for terahertz, to loop it back to the terahertz again, if we look at this Keldysh parameter, this frequency here is this term out front. If I sent in 500 nanometers, so something green, I might be in this regime. If I reduce my wavelength by a factor of 1,000, I'm going to reduce my Keldysh parameter by a factor of 1,000. So it means if in the visible for the same field strength, I might have a multi-photon process. In a terahertz case, I'm going to be drastically into the strong field regime. So far that in the process I'm going to tell you about, it would be a 1,000 photon process for it to happen. It's so unlikely from that picture that just we can kind of put that to the side. And instead, the terahertz field is going to be like a voltage. And it's going to take the Fermi level of the tip and sample and just oscillate them back and forth. So coming back to the picture, this is what happens. This terahertz pulse is oscillating, and we're oscillating between these different configurations. Now, one neat thing when we do these kind of measurements is if you sweep the voltage, that difference, and you measure what we call the dIdV, so the derivative of the current that flows as a function of voltage, that's approximately proportional to the local density of electronic states. So you can see that those 2 steps, these are these steps here. We're mapping up the density of states of the sample. Now, if we were to draw the current against the voltage, that would be the integral of that, right? So here we have this curve corresponding to that one. And the terahertz pulse comes in, acts like a voltage, oscillates up and down. Now, one challenge is that the terahertz pulse creates an ultrafast current pulse that is so fast the electronics can't measure it. So remember, that was something I said in the beginning, we need to use these pulses to measure each other and so on. So what we have to do is a trick. We make the terahertz pulse either asymmetric, or we put a bias voltage, or we find an IP curve that's asymmetric, such that the current pulse looks asymmetric. So one kind of trick from your electromagnetism class, we take a integral as a function of time of a propagating light pulse, the answer is 0, right? Because otherwise it would mean there's charge there. But the integral of this one, the current doesn't have to be 0. We use this nonlinearity, and what we call is we say we rectify it. We generate a DC component to it. And that integral as a function of time just corresponds to charge. The terahertz pulse came in, it oscillated on a junction, and the result was a charge came up and went through the circuit. And we can measure that charge. And then in our experiment, we actually have a series of laser pulses because it's an ultrafast laser. It shoots them out every microsecond. So we get a series of charges coming through our circuit, which corresponds to a current. So that's what we measure. We measure this current in our experiment. You can see that how frequently the pulse comes is important because we're measuring this average property. But this is something we can measure. And we can even measure it down to the level of, we take one electron in 1 terahertz pulse and move it between the tip and the sample. Okay, and finally, what we actually measure is we have something physically blocking it, like a fan. It blocks and unblocks that terahertz beam, and we see that current turn on and off. And so we have basically some instrument that can look at the oscillating current, called a lock-in amplifier, and simultaneously we can measure the non-oscillating current, and we can do all this at once. Okay, so it's not that much different from you've got a conventional STM. As long as you can focus your terahertz pulses onto it, you can have a terahertz STM too. Okay, good. So as Robert mentioned, this was actually something that we started in my PhD. And at the time, we just did it in air. This was like kind of this funny drawing I had done, but actually looked like what the setup looked like. And the setup, well, technically, if you looked at it now, I would cringe a little bit. It had some tape holding it down, and it had some banana clips attached to it and so on. As you'll see in a few minutes, it looks pretty different now. But this is the key property, this focus, this tip on. And we showed even we could do probe measurements of single nanodots in this case. And we could already beat the resolution of near field microscopy even in air. You can see a picture of me, as they say in sports, time is undefeated. Okay, and then, so I just wanted to highlight Viedren again. This was Viedren. He was an undergrad student who was the second author on that paper. He then took over that as a PhD project. This is Frank Hayden, who was the PI of that lab. And Viedren was a postdoc with me for 5 years, for the last 5 years. So I wanted to highlight him a bit extra. After he finished his PhD, he came and worked at MSU. This is what they continued on to do in Edmonton after I had left. That was putting this in ultra-high vacuum. And each of these dots is a single atom of silicon. And this is a terahertz-driven STM image where they've shown that they can actually get extreme tunnel currents because they have such short pulses. Okay. Since then, there's kind of been an expansion of this field to a number of groups. I only got into 2021 because now there's a lot more papers. So I still showed the slide, but I think maybe I'll have to go to this way where we do graphs and stuff now instead. But it's pretty cool. It's turned into quite a number of things. The next thing I want to tell you about is this one, which is what we did in Regensburg to look at single molecules. Okay, so next, molecules. So starting with that concept, the terahertz is driving time, we go to kind of like the full realization of what you can do with a standing time microscope in this case. You can have liquid helium temperature, you can have ultra high vacuum, and you can prepare samples in a very clean way. So here we have a gold surface, and we prepare it so it's atomically flat, and we grow one atomic layer of salt on top, and then we evaporate molecules to it. In this case, we choose pentacene. So we've evaporated some pentacene molecule. It's sitting on the salt because if the pentacene sits directly on the metal, the electronic orbitals hybridize with those of the metal, and it kind of doesn't look like its authentic self, right? Okay, great. And so this was collaboration between my postdoc advisors, Ruben Huber and Nasha Grepp, who is an expert in this single molecule estimation. Now, it's worthwhile just to look at what does this energy level diagram look like in the case of a single molecule. So here we have the substrate. Remember, we have this gap, which is the vacuum, and a tip. But in this case, we can draw the salt as part of the gap, and we can think of this pentacene molecule as living inside the gap, with the salt as part of the gap and the vacuum as part of the gap. And then we have electrons occupying the highest occupied electron orbital, and none in the lowest unoccupied. So if you're a chemist, that's familiar abbreviation. If not, that's what it means. We apply a voltage, and what happens is we unbalance the two Fermi levels, and the molecule mostly moves with a sample. You can see the slight difference. And if we get to the point where the HOMO lines up with the empty states at the tip, an electron will tunnel out, and another one will refill it from the substrate. And if we go the other way, we can tunnel from a LUMO into the substrate. So this is basically this two-step sequential tunneling process that gives us a new tunneling channel when we reach those levels. So if we sweep the voltage and we look at this DIVD, which remember is proportional to the density of states, we see these peaks, and these peaks correspond to the molecular orbital energy levels. Now, the really cool thing about this, if you set your voltage to either of those and you take a picture, the picture looks different. You trace out the electron density of that orbital. So I liked using this slide and this picture when I was when I was uh, interviewing places for my position in MSU, ultimately, because this was a T. So it's like subliminal messaging for Thailand. So technically, these are two pennies. They're kind of pushed together. And this is the highest occupied orbital, this is the lowest occupied orbital. And of course, it's not the wave function, it's the wave function squared is what you're looking at. Then the question we asked is it possible to do this on ultra-fast timescales? So this was with a bias voltage, now let's bring in terahertz and see what happens. So remember, these are the two configurations. Here, we tunnel through the gap, and here we have this sequential tunneling. So what we do is we have to be very careful with the terahertz field. We have to tune the strength of it just right. And if we do that, we can make it so just the peak of terahertz field overlaps with this tunneling channel. And so what we do is we can take electrons out one at a time per pulse, and we can choose which orbital that we want to use. And of course, we just put the tip over to the molecule. And then the cool thing that's extra that we get is it only happens at the peak of the terahertz field. And additionally, because everything we measure comes through the tunnel junction, we get spatial resolution that corresponds to the tunnel junction, which is on the angstrom scale, so 0.1 nanometers or even less. So this is the setup then, I showed you the last one was kind of schematic. Here's now the setup in Regensburg. This was a home-built standing time microscope that worked at helium temperatures, long-time vacuum. These were some mirrors and things inside that were controllable. This was the setup I built, and I didn't quite fill every screw hole, but many of them. And so what we did was we prepared this molecule of salt on gold, and we moved our tip over top, and we turned up the terahertz field, and we were happy to see a current turn on. But we weren't quite there yet. Right? What we need to do is show the spatial distribution of this current actually corresponds to electron density, and then we know that we're really taking electrons out of these orbitals one at a time. Okay, so as a reminder, this is what the picture looks like when we're tunneling through the highest occupied orbital in STM. And so what we do is we turn the voltage way down, so we don't tunnel through that orbital, and we're scanning the tip back and forth over this, and simultaneously, we're going to measure the terahertz-induced current and look at what the spatial map of that is. So this is what we see, and this terahertz-induced current is measured simultaneously with this DC current. So you can see it looks like the highest occupied orbital, yet our voltage isn't in its range. So we're basically doing two measurements at once. This one looking at the oscillating current. And now we see the highest occupied orbital again. We can also see the LUMO. This is actually 3 molecules. They were being annoying and moving around, so I pushed them together so they would stop moving. Because you can do that with STM. You can move molecules around if you like. And the cool thing about this is now that it's actually time responsive. So yes, the tip is still moving. There's still many pulses, but as you recall from the beginning, we do stroboscopic pump probe measurements. It means that we've not necessarily taken one single snapshot, but we've confined a time window that we can reference to, and so we can do a pump probe experiment. Okay, so here's our pump probe experiment. We'll come with the first terahertz pulse. We'll drive tunneling out of the HOMO, and we'll remove an electron from the molecule. And then we'll come sometime later with another terahertz pulse, and we'll drive tunneling with that second terahertz pulse. And then we'll just repeat this experiment as a function of time tau after the first one, and see how tunneling from the second one responds to time after the first one. And so, okay, hold on a sec. So first, the first terahertz pulse comes in, we take the electron out. And then the thing was, I was then had a master's student I was working with, who was very good at the time. And I said, what we're going to see is charging. We're going to charge the molecule, and then it's going to take some time to recover, and we won't be able to take electrons out until it's recovered. That's not what happened. So what actually happened was we took an electron, and this thing was very quickly neutralized by the substrate. But because of this tunneling event, the temporary charging gets kicked. And so I kicked and started moving up and down the junction. Now, the interesting thing was when we came with another terahertz pulse sometime later and moved another electron, our probability of taking it out of that molecular orbital depended on the elapsed time tau because the gap width was oscillating. So remember, if we move by an angstrom, the tip height, it changes by an order of magnitude. So this molecule is moving up and down, oscillating and changing the tunneling probability as a function of time. So here's the current we see due to the second terahertz pulse as a function of time, and you can see it oscillating. And that oscillation is associated with the binding potential of that molecule to the salt surface, such that if we then take a different surface, so basically what we do is we prepare the gold at a slightly different temperature, and we repeat, then we change the binding potential, and that oscillation frequency of dependency changes. And if we even take another molecule that's just kind of co-evaporated, sitting nearby, and we measure that one, we see yet again a different frequency, though not quite as strong as oscillating. in this case. Okay, so what we can do is even take an image like this. So here's a molecule of copper thiocyanide. And what we can do is take images as a function of time after the first pulse to see this thing moving. Now, I have to admit, this is a little bit of a convolution. So ideally what you would want is an excitation that globally excites everything, and then a probe that locally tells you what happens. In this case, I have a pump that moves with my tip and changes the excitation at each point. So I can't say that that is directly a molecule moving up and down. I'm changing how I'm exciting it at each point as well. At a given point, there's an oscillation and a pump probe measurement, but this is kind of the direction we want to go. So there was some highlight of going in this direction and doing single molecule movies. Okay, so now I'm at MSU, and this is what I want to focus on for the rest of the talk. Put myself on time. So, okay, so the first thing we did at MSU was we destroyed the room. So it was a room, and we ripped everything apart to make it an ideal space to do this teraret scanning tunnel microscopy. So this lab was temperature and humidity controlled. It has this metal plating everywhere because of the strain on the fields we were trying to get rid of. It's sort of a quasi-clean room environment. You see this is August 2018. By August 2019, we have built this thing. So we were going pretty quick. And then by February 2020, we were really taking measurements. Now, that timeline is great, but then you realize that March 2020, everything was closed. But fortunately, the first experiment I'm going to show you, we did actually before we got kicked out of the lab, which was good because then everything broke for a while after that. But now things are kind of up and running. So here you see March 2020, moments before we were shut out of the lab. You can see in the back a teraret STM image. So what we chose to look at first was a graphene-based structure. So graphene, one atomic layer of carbon. You can imagine you can roll this up into a buckyball shape or a carbon nanotube, or you can just take slices out. We would call those graphene nanoribbons. Now, to make a graphene nanoribbon, at one time, it was not so obvious how to do this. So you can see here with a nice paper, and what they've done was they cut out a graphene. But the edges are a little bit hairy, and that can really affect the properties. Fortunately, in 2010, there was a new idea, and this was to start with molecular precursors. You choose a molecule, you evaporate it onto a surface, and then you do some surface chemistry. So you heat it up a little bit, and these precursor molecules, which have these halogen atoms on them, those sort of fall off. They become reactive, they run around, they look like little X-wings from Star Wars. They line up with each other, and they form a polymer chain. And you heat it up some more, and through a surface catalyzed reaction on gold, you get what's called cyclic dehydrogenation. So you form a graphene nanoribbon, which is now atomically precise. Because remember, it came from this precursor molecule. So the precursor molecule defines the width of the ribbon, the edge shape of the ribbon, and all sorts of properties. So by choosing different precursor molecules, I can engineer different ribbons. So this is kind of a subfield in itself. Here you can see this is the first one that was made, seven atom-wide armchair graphene nanoribbon, but now you can engineer all sorts of things. And in 2016, this was kind of a nice example, but now some of the big advances have been things like people engineering topological states that run along these ribbons as well. So here you can see some graphene nanoribbons that were grown in our chamber, because we can also do the growth in the teraret STM chamber. I should maybe update this slide with some nicer ribbons. This is one of our first ones where we can see they were running into each other. One of the cool things is now if we go to particular energies and we do this DIDP imaging, like we can do for the molecules, we can see then where's the electron density, right? Like what I call the HOMO and the LUMO, we call now the valence band and conduction band. And in these STM images, you see that tends to be along the edges. That's where you really see the electron density. So we went to then do teraret STM. So here you can see an example from the conventional STM. And we sort of thought a little more carefully about this, about what the conditions are that when we're doing teraret STM. So a teraret's pulse is going to give us some tunnel current, right? And imagine it has a voltage that is going to be the same as the voltage we used here, because we're trying to hit the same orbital. But here we have a particular tunneling probability that leads to, let's say, 50 picoamps current that we can measure. If that's the case for terahertz, and the current is on for 1 picosecond and then off for a microsecond, we have a duty cycle of 10 to the minus 6. Totally not measurable at all, right? So the trick then is, remember, if you move the tip closer by 1 angstrom, you get 1 order of magnitude higher current. That means 1 order of magnitude higher tunneling probability. So what we do is we move the tip closer. I'm sorry you can't see this graph. It's a line on a long linear plot. The point being, we move the tip closer for terahertz STM measurements. Now, the interesting thing, when you then start to move the tip closer, is I showed you these probability densities, or I showed you the images of where the valence conduction bands are. From density functional theory, that's kind of what's predicted. You would see the electron density on the edges. But the only reason for that is because all the interesting stuff of the wave function has interfered by the time you get to the tip height they're usually measuring at. It actually has much, much more structure. So in the terahertz STM case, by moving the tip much closer, we actually thought, oh, we might be sensitive already to something interesting, even not time responsive, but just the electron density of these much smaller length scales. So here you can see the DIMD image, and here's the terahertz STM image. So already you almost think, oh my goodness, it's higher resolved than an STM image. It's not quite. They have probably the same spatial resolution, but it's actually that the terahertz is sensitive to much more interesting wave functions like this height. Okay, now considering the time, I'm going to sort of stick through this part, okay? So we can do imaging of this sort of all sorts of different heights, all sorts of different fields, extract what is the sort of authentic electron density of the wave function, or of the orbital, I should say, because remember the terahertz field is sweeping through these different things. And to summarize this part, what we were doing in this study was we could move the tip to different locations and measure really what at these ultra low heights is the weight of the electron density of these different orbitals. You can see we did this tomography sort of thing. So I raced through that just because I want to make sure I can tell you some stuff at the end. Robert, how am I doing for time? What's the... Okay, that's fine. So, okay, sounds good. So where we're going with this now, so we now have, we're part of a larger collaboration to try to integrate these graphing nanorobots into some sort of device. So this is sort of the imagined device that we're working on with some friends. And so now this is getting into more complex structures for these graphene nanorobots. It's not just kind of the simple ones we started with, but actually a graphene nanorobots spin chain, we call it, that we're going to operate fields on with these kind of fancy substrates. And so the hope is to make this a atomically precise qubit would be kind of the ultimate goal of it, but at the very least to characterize what our spin coherence times like for graphene nanoribbons of this sort of atomically precise bottom-up engineered type and how they might play a role in quantum information. Okay, so I did want to kind of race through because I want to tell you about one more interesting thing. And that is, you might have noticed that when I talked about terahertz stuff, terahertz excitations, here we would be doing terahertz spectroscopy. We'd be looking at excitations in the terahertz spectral range. Once I go to terahertz STM, sometimes I'm kind of telling people why I like terahertz, and then I'm not really talking about terahertz after that. The terahertz is the voltage, it's a field. Who cares about the frequency? But actually, I still care about the frequency. I would like to know what happens. And in fact, if the dielectric function under the surface is different, it's a metal or something else, what happens is the oscillating field of the terahertz pulse looks different. Because if you take the Fourier transform, you see a resonance or whatever, that impacts how we model our terahertz STM data. So there's multiple reasons for this. One, we can't model things correctly unless we actually know what the waveform looks like over a given substrate. On the other hand, if we can leverage this possibility to identify our signals at the tunnel junction with atomic resolution, with then being able to measure the waveform, then we can do spectroscopy. Like I started my PhD doing this pump probe terahertz spectroscopy, but now on the atomic scale. So it turns out you can do this pretty simply, actually. You just need a couple beam splitters to think about it. So what we do in this case is we have 1 terahertz pulse, which is strong. It's the one I'm usually talking about. And then one little baby terahertz pulse that's quite weak. And it might only be a few percent of the other one. And so what we need to do is we apply this terahertz field to some IV curve, and we generate some current pulse. And what we need to do is sort of engineer this configuration such that we get a unipolar single cycle current pulse. So I've drawn a non-ideal one here with a little blend. What I want is just a single current pulse. If I have that, and then I superimpose this field that's quite small, what happens is, based on where this one is overlapped with that one, I will either constructively add the field or destructively interfere, right? And I've only got this one current pulse, so either I'm going to push it a little higher up or a little down. So this current pulse is basically going to sample the weak terahertz field. And by repeating this and changing the time delay, I can measure those oscillations for the weak terahertz field. So here's a little simulation. Here's the terahertz pulse voltage. You can see this little one coming along. It generates this current. And now this is the differential. So we're looking at the basically on and off modulating the little field. And what we expect to see is actually the oscillating field of the little, right? Again, this isn't even a perfect case. We can achieve much higher contrast between the big direction and the small direction. So that's basically the idea. So we built such a setup. We then realized, okay, we need, if we're going to say anything about we go to a sample and see the field, we need to have a reference. So we first go to gold and we make sure we do a terahertz testing of sort of, this is a single gold atom, and we measure waveforms there. And then we go to this sample, which is gallium arsenide. And it's gallium arsenide doped with silicon atoms. And the silicon atoms replace the gallium atoms, typically. Once in a while, they replace the arsenic if they're feeling kind of fancy, but typically they replace the gallium. Additionally, there are gallium vacancies at the surface, those missing gallium sites. And as we scan around and we look with our terahertz STM, we can see this image with topography looks totally different with terahertz STM. In fact, there's only one spot it cares about, right in the middle of this. Okay, now, if we measure these waveforms, we see in the pristine region some sort of interesting waveform. If we go to this green, we see yet different pulse, but spectroscopically, they're not that different. However, if we put the tip on top of this bright blue dot, we see a very, very strong resonance. And so now this is the terahertz field that we measured just with the tip located there, which is 0.2 nanometers away, right? So this is orders of magnitude record in spatial resolution in terms of near field microscopy. I'd have to think about how many orders of magnitude percent. But the main, more interesting point is that there's actually a resonator here. And that we're able to coherently drive it, and maybe surprisingly that it's actually so sensitive spatially. We've kind of thought a bit about this. Is it actually partially because the tip impacts it where it is? So we can compare by measuring, taking the Fourier transform of this field in the time domain and dividing our reference with gold, we can see what basically the spectra look like. And then we can even zoom into this thing. We can take spectra as a function of space on the, now we're into picometer scale, and zoom in on this scale. We can really measure what's the Q factor of this thing? Where does this resonance evolve, and then where does it go away? And of course, you might wonder, well, what is it, right? That's kind of the more natural thing. And what my postdoc said, Adrian, he made a nice comment, which was that every time you find something, there should be 30 years of research already on that thing. So it's quite handy. So this is a relatively recent paper, but defects in gallium arsenide have been a very popular topic for many, many years. And there's a particular thing in gallium arsenide that's been postulated but hadn't been seen directly called a DX center. This corresponds to donor vacancy complex. So what it means is you have a silicon replacing a gallium, and then you have an empty gallium site, and they form a complex. Now, within gallium arsenide, that's not so energetically stable. But remember, we had this sort of low potential area where we were looking. So you can basically find regions where it's stabilized at the surface, even though maybe it wouldn't be without those other defects happening. Now, the really cool thing about this paper that I really like, not only did they calculate where the electron density should be, they calculated the resonance of it. So they said there should be some vibrational resonance correlated with the motion of the silicon atom towards that vacancy. And this one right here, the DX center, this is 1 terahertz if I translate the frequency from omega to terahertz, and this is basically what we see. So then, of course, we have additional other measurements kind of correlating, showing that, for example, we can move the tip on top of this thing, and we can hop the silicon out of the vacancy and back and forth. We can push it back and forth. Yeah. So anyways, we're pretty excited about that. We've now since been doing things like pump probe measurements as well, where we optically excite the sample and we'll look at single defects and then measure how does the pump probe response, that is the decay of the optically photoexcited surface, depend where we put the tip, whether it's over, in this case, a gallium vacancy or nearby the pristine surface. And we actually see different time dynamics based on where we put the takeaways about terahertz scanning tunneling microscopy, which you heard about today. So terahertz scanning tunneling microscopy, number one, It uses the oscillating field of a terahertz light pulse to control tunneling across a tunnel junction. By doing this, it achieves simultaneous atomic spatial resolution and ultra-fast temporal resolution of the surface. And from this, we can now do a number of things. And what we talked about so far today was that we can see these electron densities in atoms, molecules, and solids. We can see them move, such as this silicon vacancy complex or the pentacene molecule moving up and down. And the thing that I kind of breezed by at the end is because we have these strong fields, those strong fields are strong enough that they can actually control the material itself, control the material as well. In the case of tungsten telluride, that was by driving this topological phase transition at the surface, but that requires more kind of study. Okay, finally, okay. Something's up, click. Okay, so finally, I just wanted to thank you again for coming and for giving your attention. And I wanted to highlight once more the people in my group and the people who also helped pay for it.